Our final speaker for this session is Catherine Moyes, who's going to introduce a new project, which is the main component of this. So, Catherine.
Thank you. I'm going to talk today about our plans to model spatial temporal patterns of insecticide resistance in malaria vectors. And the reasons that we want to do this are threefold. We want to map resistance so that we can fill in gaps in the data. We want to investigate the drivers of selection using a cartographic approach. And we want to generate outputs that can be combined with estimates of the impact of insecticide resistance. So our starting point is that we don't know enough about the factors that lead to variation in resistance and the relationships between those to model insecticide resistance without taking an empirical approach and using large amounts of data, because what we want to do is learn from the levels of the prevalence of resistance that we know exist in certain locations and times to then predict what's happening in other places. So to do that, as I say, we need large volumes of data, and we've spent the last few months putting together a database of these phenotypic data. So these are bioassay results. And we've taken them from the published literature, and we've contacted people who have unpublished data sets, and this is where we're at today. We have over 14,000 data points for mortality, which is fantastic. It's a great starting point, but there are a number of issues that we need to address in the analysis of these data. So to start with, just looking at this map, you can see that the distribution of data we have is highly clustered, and if you zoomed in at every scale, you would see it's clustered, and this comes to the point that's come up already, that we have results where entomologists work. So that's the first issue. The second is that this data set that I'm showing up here, I've put everything on one scale. It looks like it's one measure of insecticide resistance, but in fact, this is covering 4 classes of insecticide, and if we split those out, then of course the data numbers for each comes down, but it's important to consider the classes and the individual insecticides within those. If we look at these maps for the 4 main classes of insecticides, you can start to see that there may be some differences going on there. So for example, organophosphates, the levels of resistance look low, or mortality looks high, compared to, for example, organochlorines, but maybe the organophosphate data is simply older, and there are actually temporal trends in these data too. So in addition to taking account of spatial factors, we also need to include temporal trends. This is now just a box plot looking simply at pyrethroid bioassay data. And for the pyrethroids, we have data going back to the 1980s, but not much of it. And so this is just showing the years where we have over 100 data points. And on the face of it, it looks like, as we would expect, there are increasing levels of resistance or decreasing levels of mortality. But again, we need to be careful, because this data set does not come from a single systematic survey of the world where we've looked, had one sampling design and looked for resistance. These come from multiple studies with multiple sampling designs that have been collated and put together. So we could have differences in the data we're looking at for different years. So early on, there may be more data from Malaysia, later on from West Africa, and so on. So it's really important that we're considering the spatial and temporal distribution of the data when we're doing this. So we have to consider issues of time and space and the insecticide used and the classes. But it's further complicated by the fact that, as we all know, malaria is transmitted by many mosquito species. So this is going back to the original data set I showed for all of the insecticide classes. And if we now split this out by species, this map, there's no key here because you can't possibly try and show 74 species and complexes, but that's how many are represented within our data set. It's not quite as bad as it looks, because many of these, there are only 1 or 2 data points, so around 30 species or complexes are represented in the main data set, but that's still a lot. And we need to consider differences between species and complexes, because as we've already heard, they have different genetic backgrounds, they will differ in the chance of resistance arising in the first place and its spread. So we need to consider that as a factor. Not only do these species differ in the genetic background against which resistance is arising, they also have different behaviours. So we may be able to classify the species data we have linked to our phenotypic data based on behaviour. And in one example here, we're showing the feeding and resting indoors and outdoors. And if we classify the species in this way, we can start to see a simplified version of the species map. But it's important to note that this isn't a map of where these behaviours occur. This is a map of where we have bioassay data that is linked to species data for which we have behaviour data. So the number of data points that we have now has dropped down to just over 6,000 from over 4,000. But it is still an important factor to consider. And another way that species differ is in their habitat preferences. And we are interested in not only the species encountering insecticides used in public health, as represented here by feeding and resting behaviour, but also, for example, larval habitats and agricultural pesticides. So for individual species, we're also mapping these species to get down to their habitat preferences and to incorporate that into this analysis. It's not just malaria vectors, of course, that encounter insecticides in houses associated with people or in agricultural environments. So I'm just going to go on a slight detour here. This isn't part of our primary core analysis, but just to mention that it's possible that there may be relationships with what are going on with other disease vectors, not just malaria ones, because they share the same environments and some of the same behaviours with some of the malaria vectors. So in this example here, the worldwide insecticide resistance network for the major vectors of the arboviruses of importance to human disease, which is a rather long title. They're funded by WHO TDR, and they're looking at resistance in Aedes aegypti and Aedes albopictus. And in this slide here, you can see the bioassay results they've collated for Aedes aegypti, where they've looked at delta methrin resistance in adult bioassays. And one point to note is that you can see that they have a lot more data for the Americas and a lot less data for Africa compared to the data that we have for the malaria vectors. So it's debatable whether information from other disease vectors can inform what we're looking at with malaria vectors, but it is something that we may look into. So back to the main topic of this talk. So having talked a little bit about the data and the confounding factors in that, I'm going to move on to the modelling approach that we want to take. And our starting point will be a Bayesian geostatistical model that's been used previously to model parasite prevalence of Plasmodium falciparum, which is the example here, but also Plasmodium vivax. This model incorporates spatial dependence, but also temporal trends, and incorporates covariates. So a lot of the things that we want to take account of and cover. And what you can see here in the maps at the top, they've produced not just maps that show spatial variation, but the maps are from 2 different years, so they are also showing the changes in time as well, as shown in the bottom right there. So this is the starting point. This isn't the exact modelling framework that we will use, because there are some similarities but also some important differences when you're considering Plasmodium falciparum infection prevalence and the prevalence of insecticide resistance. So briefly, this modelling approach, one of the advantages is that it takes account of the patchiness that you see in malaria prevalence data, and this is due in large part to the patchiness you see in vector populations, and we might expect to see something similar for insecticide resistance too. Also, a point that I haven't mentioned so far, we all know insecticide resistance bioassays use a range of different protocols, and the same is true in the world of parasite prevalence, where you may be using microscopy or RDTs and so on. So again, we have some comparable issues to address here. And for both parasite prevalence and insecticide resistance prevalence, then there are temporal trends that you need to take account of. But there are some new challenges when we're considering insecticide resistance, and I've talked about the fact that we have multiple species here. So Plasmodium falciparum was mapped globally, as was Plasmodium vivax. We can't take the same approach for insecticide resistance in vectors. We have multiple vectors in the same species, but then we also have very different vector composition in different parts of the world. You don't find Asian vectors in Africa. So these are all factors that we need to consider in developing this modelling framework further. Finally, the data requirements. So I've already discussed a number of ways in which there are extra factors that we need to include when we're looking at insecticide resistance, but at the moment our full data set is around half the size of the Plasmodium falciparum prevalence data set. So there's some challenges in there, and if anyone out there has any data we don't already have, we would love to receive it because it's all important in this approach. Coming on then, we have started to do a little bit of preliminary work. So I've talked about a whole range of confounding factors that it's important to take into account. And it's very important to note that this map has not done that. This is something very preliminary, mainly focused on the spatial dependence issue. And the good news is that we have found spatial patterns to model. So it is worth continuing. But this, as I say, is just a first step in exploring the data and how we're going to model it. So I've talked a lot about the kind of confounders that we need to take into account, but we're also interested in incorporating covariates, and this comes to the second aim of our work, which is to investigate potential drivers of selection. And so in our modelling framework, as part of our characterising the spatial temporal patterns of resistance, there are a range of covariates that we want to consider, and we're not going to assume anything about what their role is and the relationships they have with resistance, but they will be environmental factors. Insecticides used in public health, we've already talked about the potential for them to play a role. And then, of course, pesticide use in agriculture, which is not an easy thing to get hold of a global data set describing agricultural use of pesticides. So we're also considering other factors linked to pesticide use that may be useful. So what we have here on the bottom left is the proportional cover of croplands, and that's specifically annual crops rather than all year round. And also some of our own work on the variation in distribution of bednet use in Africa. So these are the kind of covariates that we want to incorporate into this model. So coming back, this is my very first slide. Again, fleshing out the points I've been talking about. So we want to characterise spatial temporal patterns of insecticide resistance in different regions of the world using a geostatistical approach. So we're talking about regional maps rather than something global, and we want to look at the drivers of selection that I've just talked about. And then importantly, when it comes to providing outputs that can feed into models and work on the impact of resistance, the outputs from this particular model won't simply be an estimate of resistance at a particular place. They will be a posterior distribution of estimates. And so we can then provide measures of uncertainty that can feed through to other models. And then finally, an important point is that all of the data that we're pooling together for this work will be released. Some of it came from the published literature, and that will all be released for everybody to use. Some of it's unpublished, and where we have permission to, we will release it. And if we don't, that will be held confidential. But all of the data that we can, that we're using in these analyses, we'll also make available to everybody else. And then the outputs, the posterior distributions, the estimates coming out of this model, will also be made freely available. So finally, I just want to thank the funders for this work, the Wellcome Trust. And then we have our core team in both Oxford and Liverpool. And then we also have the all-important data contributors. So everyone listed here has either given us unpublished data or has clarified and provided extra information about their published data, but not forgetting the people who published all of their data, and which we've now extracted and incorporated. Without them, we'd be nothing, and so thank you.